Ladies and gentlemen, welcome to our first ever Jay on the Beach session. So I welcome you to what's going to be a fantastic 2 days of technology, of meeting people, and so on. Before we start, I just want to say a few words of thanks to some people that have really made it possible to do this. We're in the lovely venue here today for the Tematica? I can't pronounce it very well, but the Tematica location. The team here has been fantastic in helping us. I'm sure you appreciate the value of the great location here and also the more historic building in the other area. The province and the governments of Malaga have been fantastic and supportive in both all our efforts as a community, as a technical community, to run these events. So we are very grateful for them. And also the technology park. Many of the companies that you see here today, many of the sponsors come from the Malaga Technology Park, and they again have been incredibly supportive in enabling us to work this event. So thank you very much to all of those folks. So this kind of event doesn't work just by organizing it ourselves. So I'm Nikki Hills, and I come from Velo, the team that's hosting this. However, there is actually a whole raft of others that have helped us organize, and a number of the local technology groups have got together to arrange this event. You will see on your agenda that this evening there is networking events with a number of these guys. There'll be others coming in this evening from the local area to join us. I really would encourage you, come, network, join in. They're welcoming, any visitors to the area. They would love to have you come along for their networking events this evening to meet new people. So please do come along and support our organizers this evening in our events. There will be beer, there will be music and so on. So come and enjoy. We also have a whole set of sponsors that have enabled us to be able to run this at the low cost that we have. So we're very grateful to them. You'll see a number of them in the old building in the main hall set up. So again, have a chat to them, but thank you very much to all of our main sponsors that have helped us. And we do have a short message from one of our platinum sponsors, Jelastic.
Jelastic, DevOps platform with containers. Jelastic Cluster is a set of hardware nodes with a DevOps platform running on top. It can be configured within one data center or even several clouds. Each hardware node divides into a number of isolated and highly secure containers with users' applications. They can be vertically scaled using Jelastic Resource Unit Cloudlet that equals to 200 MHz CPU and 128 megabytes RAM. Jelastic platform measures how many resources the application requires and allocates them automatically according to the load changes. You just choose the container with the required stack and set the maximum limits. The rest will be done by Jelastic automatic vertical scaling. As a result, you don't pay for unused resources and don't worry about the load spikes. To make the cost even more attractive, you can set a number of discounted reserved cloudlets that are used by your application on a daily basis, regardless the load. Even more, you can scale your application horizontally, adding new servers just in a mouse click. Set up the load balancing and database replication with an intuitive UI and get your application environment up and running in minutes. Advanced scalability and full control over your project with Jelastic.
So thank you very much to Jelastic as a major sponsor alongside Velo of this event. We very much appreciate it. So what are your responsibilities for the next 2 days? So first off, learn lots of new techie stuff. We have 48 international speakers here. Make the most of it. Go to the sessions, ask questions, catch the speakers afterwards. So thank you to all of those speakers for joining us. Meet some interesting new people. There are over 300 people here over these 2 days. all down and dirty techies like you that want to have conversations about technology. So go to the meetups, grab people over lunch and coffee breaks and so on, meet new people, make connections, and make that work. And probably the most important of those is have fun. You know, we have beers tonight, the sessions, and when you're meeting people, please enjoy. That you will see that there is a lot of people around wearing these t-shirts. Our job our responsibility is to make this happen for you. So if you have any problems, any issues, if you can't find your way to somewhere, if you're not having fun, then these are the people that you need to ask or complain to. Okay, so please feel free to grab anyone with one of the Velo Love Data t-shirts on if you get stuck, lost, need help, or just to give us feedback on what you think, how it's going, what's good and what's not so good. So, without further ado, I'm going to hand over to Sergey, who is the leader of Sergey, who's the leader of the Microsoft research and open source project that's really building scalable distributed systems. And he, having started the project in 2008 and open sourced it in 2015, now has a really vibrant community around the project. So we are thrilled to have someone who is both a great technologist, but also sharing open technology with the world and with you to be our first keynote speaker. So welcome.
Thank you.
Over to you.
Thank you. And welcome to Malaga, this beautiful city and beautiful venue. I'm going to be talking about Orleans, which is the framework for building, we call it Halo scale systems, primarily in the cloud, but not necessarily just, oh, sorry, why did it move? The point was to wake you up and also to give you an idea of what we mean when we say Halo scale. So let's watch this video quickly.
Halo is a rich, immersive story with millions of loyal and dedicated fans. We deliver an exciting and engaging experience to these fans. They need to know what the hot playlist is today. They need to know what the challenges are. They need to know where their friends have been, what their friends have been playing. Have their friends gotten more medals than them? They need to know all of this, and they need to react to it and interact with their friends in real time. We need to deliver hundreds of thousands of updates per second to millions of players across the Halo universe. We need to get them the right information to the right device at the right time. There was nothing off the shelf that solved the problems we needed to solve at the scale we needed to solve them. So we turned to Microsoft's Extreme Computing Group.
Hundreds of thousands. Oops. What happened? I didn't do anything. Oh.
Halo is a rich, immersive story
with
millions of loyal and dedicated fans. We deliver an exciting and engaging experience to these fans. They need to know what the hot playlist is today. They need to know what the challenges are. They need to know where their friends have been, what their friends have been playing. Have their friends gotten more medals than them? They need to know all of this, and they need to react to it and interact with their friends in real time. We need to deliver hundreds of thousands of updates per second to millions of players across the Halo universe. We need to get them the right information to the right device at the right time. There was nothing off the shelf that solved the problems we needed to solve at the scale we needed to solve them. So we turned to Microsoft's Extreme Computing Group.
Hundreds of thousands of requests per second across thousands of servers in real time. These guys are crazy. But in extreme computing, those are the kind of challenges we like to tackle.
So this is an old video, but I still like it because Hoop Somwa, my partner in crime there, he gives this idea of what it takes to build an experience like Halo, where you have millions of very dedicated, passionate fans. By the way, he now has a new job as a technology advisor to CEO of this 40-year-old startup in Redmond, Microsoft, Satya Nadella. He's a great guy. So we're going to be talking about cloud, and we also I'd like to play the Name the Tune game. Who knows Name the Tune? So when you see something in codes, if you can name the tune, just yell it. Or at least if you know the band that played, yell it too. And whoever guesses the most, I'll buy you a beer later today. Right? So this one is a hard one. Anybody? Oh, that's from David Bowie. So we're talking about the cloud. Cloud really changed the game. So what is cloud? The cloud is the ability to rent hardware very fast and in a very large scale. So those kind of resources used to be available only to huge companies or to governments. Now anybody with a credit card can go and rent thousands of machines instantaneously and run lots of the workloads that were unthought of before. So cloud is the real thing. It's not a fad, it's not a marketing thing. But the issue with the cloud is once you get this power, with great power comes great responsibility. How do you build software that runs on these machines? How do you deal with distributing your computations? How do you deal with failures that are inherent in the cloud environment when machines can disappear from your cluster just because they get rebooted or because they failed or because the cloud provider decides to migrate the machine? How do you deal with all of that and move from programming a single machine, single process applications to building these distributed high-scale systems? So that's a big challenge. Hope it will work. As with many other cases, here you see, oh, why is it moving so fast? Oh, something is wrong with my clicker. So you get all these analysts and consultants that come and tell you what, I don't know why it's switching. There's something wrong. Make all these claims. Like, for example, Facebook was built with PHP and MySQL. That means if I use this technology, I can build next Facebook. Or SOAP was supposed to solve all the web services problem. If we just build SOAP-based services, everything will be solved in the world. Like the hottest technology or language that people talk about is Go, because Docker was built in Go. Why don't we use Go and solve it? And then people come and make some other claims about what you need to do. The last one was my favorite one by Mary Jo Foley. Wait, I'm really having a problem with this clicker. So Mary Jo in 2010 said that Orleans is going to solve the problem. I want to show you this picture. There is something wrong with it. Okay. Or is it just slow? This picture. So, is there a different clicker? So there's this guy, the brilliant guy, Kyle Kingsbury. And if you've never heard his talk about Jepson, Call Me Maybe, I really encourage you to watch it. Where is this picture? This one? No? You gotta plug it in. But it's over there. Sorry, we have some technical issue. Flipping slides. That's what happens when you have complex. When you have complex animations. So he showed this picture. I'll try to stick to it. It's a rainbow at the top at the API level. So what Kyle did, he took alone in his apartment on the machine, like a beefy machine, he built the system called Jepson. He takes a commercial open source distributed databases like MongoDB or Elasticsearch, runs them in the scenarios where nodes get partitioned. So they lose connectivity or get shut down out of the blue. And he runs workloads and he measures and records everything. And he showed in his blog, Jepson, Call Me Maybe, that pretty much every single database that's out there, open source distributed database, they fail in these scenarios. Okay. No. So underneath these beautiful rainbows and unicorns, there is tire fire underneath. So underneath, when there are failures, things don't work. So you get all this information and trying to decide what to do. I think one way of looking at the challenge of the cloud scale is seeing it as a triangle. So you have a problem of compute, distributing compute, managing compute, expressing compute. You have a problem of state and problem of connectivity. So these are three areas that need to work in concert to solve real business problems. And there are many choices. It's all about trade-offs. Anybody knows what the quote is from? Because you need to sacrifice something to get something. It's from Jesus Christ Superstar. Whether you're stateful or stateless, whether you run batch computation or interactive workloads. Because if you can afford to run batch, it's easy. If you can afford to do compute in minutes and in hours it's very efficient to do it in batch mode. But if you need to return results, like in Halo case, in sub-second latency, you cannot do the same thing. So the whole thing is about making all these trade-offs. So let's see if this will work. No? Is it switched on? There isn't. I think now I have 2 clickers, but none of them work. Okay. So this is one approach of building a system. So we call them hero developers, or in developer division, Microsoft, we used to call them Einstein-level developers. These are people that can build, are able to build these complex distributed systems and solve these hard problems. Because at the end of the day, somebody built Google, somebody built Facebook, somebody built all these distributed databases. The problem with hero developers is that it's hard to find. And even if you find them, it's hard to hire because they're all happily employed. There are few of them. And the majority of developers we realistically can hire, they're not hero developers. They're good developers. They're very successful building single machine systems. But it's hard for them to get to that kind of level of complexity. And even when you have hero developers working on the problems, even they are not immune to making mistakes. If you look at the history of all those successful properties, like on Facebook, Google, LinkedIn, they all show the same pattern of rebuilding the architecture entirely 3 or 4 times as the load was growing, because they were running into walls of limitations of their architectures. Why is it not where I was? The new one? Okay, the new one works. So when it goes back to business, here's our business partners, how we look at it. They look at it not from a technology perspective, look at it from time to market return investment. So they need to build solutions fast, and that pace is increasing. So if your business is walking, your competitors may be running. So like that quote from Alice in Wonderland, if I paraphrase, in order to stay where you're at in competition, you have to run just to stay where you're at. If you need to get ahead of your competition, you need to run faster. So you need to be able to produce these solutions fast. And they need to be inexpensive, relatively inexpensive, so you can build scalable systems. Scalability is important by itself because if you want to grow your business, you want the cost of acquiring additional customers to grow linearly with the number of customers. If you multiply it, if you had 1 million users and in a couple of months you get to 5 million, you want your cost to increase 5 times, not 10 times. It's very important to be able to scale the business as success of your offering, of your product grows. So that's kind of what we focused on in Orleans, how to solve these 2 problems. So if we look at how we've been building services, online services and other services for the last 20 years or so, that's the model that almost everyone used. The stateless model, you have 3 layers, a 3-tier, N-tier architecture. You have stateless front ends. They admit users, they authenticate users, authorize their requests, and then forward requests to a middle tier. The middle tier server talks to storage. This is where the source of truth is. They load the state, perform operation, route state back. So it's very easy to scale. You end front ends, you end middle tier servers, and you can process more requests, right? It's very easy to think about and build. Anybody can build it. The problem is with storage, right? Storage is the bottleneck. So if you keep increasing load in storage, it's very difficult to scale storage. If you have to go to storage for every read, you read user profile or other piece of data every time a request comes in, without remembering that you already processed this request maybe a minute ago, maybe a second ago. Oh, we keep switching slides. So the industry added the cache layer, like memcached Redis solution, as a solution for this. So instead of reading from storage, you read from the cache, which gives you much better read throughput. The problem with this is still that now you need to talk to 2 storage solutions. They're very different. So your original cold storage has semantic consistency guarantees and semantics. When you switch this data to cache layer, you lose almost all of it. And now you have to talk in parallel and then try to reconcile changes that you're making to the cold storage with what you have in cache. So what ideally you want to have a stateful middle tier. What you need it for performance so that you can have this load. And you want a stateful middle tier that will combine both, to combine these 2 pieces of middle tier code and state that you bring in memory. And that's kind of where we approached it. Anybody knows the quote? Looks like I'm going to win Name the Tune contest today. It's from The Doors. So this is the two pillars that we defined for Orleans when we started. We want to have a programming model that is very easy to use, yet very powerful, that would work for a wide range of developers, for hero expert developers and for normal single machine developers, that anybody could benefit from it. We want it to be qualitatively easier. It's not 20%, not 30%, but we want it to be much more powerful. The only way I personally know how to make developers more productive is to have them write less code. So if you have a developer write 5 times less code, I would claim it would be about 5 times as productive. But also if you have developer write simpler code, that makes them as more productive as well. At the same time, we want to have these patterns, well-known patterns encapsulated in the model that would drive developer down the path of likely success, so that the code will scale through orders of magnitude of load. If you multiply your user base by 10, by 100, by 1,000, you don't have to go back and redo the architecture. You may need to optimize a couple of things, but in general, your general design should work. Those were the two pillars that we defined for Orleans when we started. So nothing is new, really. All the ideas were invented before. So what we based Orleans is on the notion of the actor model. Who in the audience knows about the actor model? I know Roland knows. Oh, great. So for those who don't know, it's very simple. So actors are kind of like distributed objects. They're isolated entities that don't share their state directly with other actors. So in order to change state of an actor, you need to send a message to it. So it's kind of like isolated objects that send messages to each other, can create other objects, more or less. So it's a very powerful model. It wasn't invented as a concurrency model. At the time in 1973 when Carl Hewitt came up with it, that was for solving concurrency problem for artificial intelligence applications. Of course, it was single machine at the time. It wasn't even distributed until Erlang in late 80s, early 90s popularized it, and then OTP added some distribution. So in the new world, there are other benefits of the model that were not obvious maybe at the time. Because of the message passing, you can easily place these actors, these objects on different machines, and they have no assumption about other actors they're talking to be on the same machine. So you can easily place them on a distributed systems and without worrying about their physical addresses. That's sort of where we started. We published a paper. If you search for Orleans MSR paper, it describes the model in details. The root of it is the notion of the virtual actor. So before Orleans, the traditional actor model implied that you had to create actors explicitly. And in the distributed world, when you create an actor, you had to specify where actor is going to live. So with workloads like cloud, where requests come concurrently to different front ends because they have a load balancer in front, it's very difficult to organize some consensus about where the actors are, whether the actor for this user or for this session exists. So you need to implement this coordination algorithm mechanism, and they're not easy to get right. So the virtual actor model changes that. So in the virtual actor model of Orleans, actors exist the whole time. So we took virtual from the virtual notion of virtual memory. When you talk to memory in general in operating system, you're not asking whether this address is in memory or in the page file. You just try to update something in a particular memory address, and it's operating system's job to find whether the page is, and if needed, load it into memory. And if the page is cold, nobody touched it, it offloads it to page file. It's the same idea here. So you can program as if all the actors, the whole namespace of actors always exists in memory. And then the runtime, the Orleans runtime, which is the layer that runs on all of these machines, it's its job to do heavy lifting of figuring out what runs where, create actors as needed. You can read details in the paper. So this is how it looks in code. So you look at, you need to define the interface. So user is the interface of the grain. We define a different name for actors to avoid confusion. So we call them grains to differentiate from the notion of Erlang actors or Akka actors, because they have different properties. So you define the interface which includes one or more methods. One requirement is that all those methods, they're asynchronous. They return a task. Who knows what task is in TPL? It's essentially a promise. It is a promise. So it's a promise for a future value, saying, I return a task with string. Sometime later, I'll have a string for you. For now, you have a handle for that future result. So it's kind of like futures in Java, but you don't have to block a thread. You can have better constructs interacting with it. So here's how you use a grain. So the first line, it calls a static factory class and calls give me a grain, give me a reference to a grain of this type that implements this interface with this identity. So each grain of a particular type has a key. A key can be a GUID, can be an integer, can be a string, a combination of them. So by knowing a class, essentially, so it's like object-oriented, you know the class user, and you want know identity, like user ID, user GUID or integer, you can say, give me a reference. And that call immediately returns a proxy object, which implements the original interface, right? And we can make a call right away. So this call, as we defined, returns a promise for a string. It returns immediately. So with this time, like you see, there is no code to look up or create the grain. We assume the grain exists. We assume it's in memory. And what happens behind the scenes, there is this life cycle of the actor where it can be in persistent store, or it can be in memory, or it can be transitioning between the two. When the first call comes for a grain that's not in memory, the runtime finds that we don't have an instance on any of the machines in the cluster, decides to create one, decides where to place it, and reads state from persistent store if necessary. It runs through some initialization process. It's kind of like constructor method. And then grain is in memory. And after runtime decides that this grain has been inactive for a period of time, which is configurable, for example, for 2 hours nobody called the grain, can decide to deactivate and collect the resources and remove it from memory. And all that is triggered by calls into the grain. So when you implement the grain, again, you implement a normal .NET class, which extends a base class of grain and implements one or more interfaces. So you can talk to the same grain over different interfaces. And it's a simple implementation, and I'll show later like this beauty of async and await keywords. So we just construct a result and return. But this code runs on a different machine from the caller. And all the machinery of delivering a request, getting results, delivering back, and saying, hey, you got your result, is done by the runtime. Notice also that there is this counter, private counter where I count the calls. The important thing here is that all these methods, they run in a single thread environment. So when you write this code, you're not concerned about different methods of the same object, of the same grain running in parallel. You don't need to do any locks or any semaphores, any threading related constructs in the code. You're guaranteed by the runtime that anytime your code runs, it owns the state. So I can do ++ easily and not worry that there is some concurrency here. So if you go back to this picture, the whole life cycle is managed automatically by the runtime. But what triggers activation of the grains are calls from clients like front ends or from other grains. So it's completely disjoint. There is no central location, central place to control it. It's all driven by code itself. One aspect that is not obvious, but it goes from this notion of the actor model, that when these actors run, they really represent those entities like users, sessions, devices that were active, actually did something recently, just in a period of time until they get collected. So that gives you this idea that what's in memory is just a sliding window of the total address space of possible actors. To give you an example, if you have, say, 30, 40 million of people that bought Halo or Call of Duty or some other games, it doesn't mean they're all online at the same time. In fact, you probably won't find more than 1 or 2 million of them at any point in time online. So when you run these services, they have actors, grains in memory, only for those players that actually turn on their consoles or their mobile device or their application. And as they turn them on, as they stop playing, their actors, they get collected over time by the runtime. So you have only a subset of grains active in memory, and only the resource used only for them for that subset. The Orleans runtime runs as an overlay, of course, on top of the physical resources, like physical servers or virtual machines or whatever you use, because you can deploy it in the cloud or not. It is aware of that, and it controls, understands the state of the cluster. So it monitors machines. So if a machine goes down, like for example, it breaks, or your cloud provider decides to patch the machine and reboot it, the Orleans runtime understands that that machine disappeared. It understands what actors, what grains were running on that machine. And then if there is a new call to some of those grains, they will be placed on the remaining healthy servers. So that recovery happens automatically. As a caller, you don't have to worry about it. You don't have to know what happened to the machine. All these failures, they're handled by the runtime. And then if this machine later comes back, for example, got patched and rebooted or got repaired, it joins the cluster automatically and it started being used by the runtime to place more workload on it. Again, you don't write any code for that. That's all done by Orleans runtime. And the best code you can write is the code you don't write because you don't have bugs there. Right? That's the goal, to write less code. Let's look at another example. Let's say we're building a social graph, social network. And by social network, I don't narrowly mean like Facebook's or Twitter. A lot of stuff is really social graph. The gamers, it's a social graph of people joining per game and having friend relations, things like that. But also in IoT, you have devices that are out there, but they control the same room, and they control the same factory floor. So they kind of join into the social graph. It's just a question how static or how dynamic graph is. On the gaming side, the graphs are very, very dynamic. In the manufacturing floor, they're probably very static. But you have kind of the same sort of relations. So let's say I have an interface with a method to add a friend. Here's how I implement it in Orleans. Like in this code, the first two lines, they get references. We call them grain references, reference to 2 grains for me and for my friend. And then I merely pass a reference as an argument to the grain. So this grain reference, because it's a logical address, it's not the physical address of the machine, it's not a URL, it's not IP address or port, it's just the logical identity of the actor, so it's always valid. That's why actor, the grains, they live forever. Which means I can save this grain reference to database. I can send it over the wire. I can save it and read a week later, and it'll still be valid. I can still make calls to this grain. So that's why we call them virtual actors. They're always valid. But also notice that we can handle exceptions here. So try catch. Notice that I'm making the call remotely, but I can handle exceptions here. Just to illustrate it better, let's look at this picture. If I can switch slides again. Let's say we have a front end that makes a call to a grain A that, as part of processing the request, needs to call a grain B like another user, or needs to call another grain. The B needs to call C because that's some coordination grain. And say C throws an exception. There is some failure, logical or physical, there is an exception during this call. If you write no code in Orleans, that exception will be delivered automatically to the B, which runs on a different machine. Within B, you can handle with try-catch or not. If you don't write any code, that exception will go to the caller of B to A and eventually to the front end that caused this whole thing. So effectively got distributed asynchronous try-catch semantics that works across the cluster of machines, across machine boundaries with no code. So you only put try-catch where you want to handle errors. And usually you want to handle them at the very top because at the bottom, there is nothing you can do. Are you going to retry this call or not? Usually you need to handle it before you return something to the end user. So again, that reduces the amount of code you need to write. You don't need to propagate any failures. They get auto-propagated for you, as if it's running within a single process. That's the illusion you get. So there's another example, still staying on the social network social network example. So say I need to return a method that gives statuses of all my friends. For example, I need to render an HTML table with my friend and their status, right? And imagine I have 1,000 friends. If I need to call 1,000 grains and say, give me your status, and the latency of each call is 10 milliseconds, if I were to call them serially, it would take 10 milliseconds times 1,000, 10 seconds, which is usually not acceptable for a user experience. So what I want to do, I want to send this request in parallel and process them all in parallel. So to fan them out, this is all I need to write. This is a for each loop and say, friend, get status. Remember that this call returns a task. It's a promise for a future result. It returns immediately. There is nothing that's done yet. So this loop runs quickly, fans out 1,000 requests in my example, and then with these constructs of async and await, this is the beauty of C#5 with these keywords were added. The rest of the method gets turned into a continuation. So this is a continuation that runs asynchronously when all the results come back in. So what I get, I have parallel fan out to all of my friends. And if I have enough parallelism in the system, I have enough cores, enough machines, in the ideal case, all those requests will happen in parallel, and the latency of the whole call will be 10 milliseconds instead of 10 seconds. So this is just one example of what kind of patterns it's easy to implement with just a few lines of code in Orleans that run across the cluster of machines. They can be pretty large. So you can leverage parallelism in the system without doing any synchronization, without writing any multi-threaded code, but just using these very simple primitives. I was very proud when Carl Hewitt, the original inventor of the Dactyl model, wrote this last year, that Orleans took Dactyl model step forward toward the goals of developers not being concerned with low-level, I'm paraphrasing, low-level system details. That's essentially what we're doing. So we're raising the level of abstraction and allow to do things much more simpler. Another feature we have is declarative persistence, because in some cases you have state just in memory, but in most cases you also have the state persisted in some storage and database and whatnot on key value store. This is how you do it in Orleans. You define a property back as a state class, a set of properties that constitute the state of your grain class. And then you simply pass it as type arguments when you declare your grain class. Because of that, you get this method, write state async, that one call is enough to persist your state in a database or in some other storage. And there is this declarative notion to link it to configuration to point to persistence provider. There is a provider model underneath. So you can use providers, one of those that we included, or some that built in a community. And you can switch from, say, SQL to NoSQL store without changing any application logic. You may need to migrate your state in storage, but you don't need to change your code. The code will look exactly like that. So that's another abstraction inside. The feature we added last year, I think, or the year before, virtual streams. So in many cases, as you can imagine, in addition to return a single value from the call, you need to return a sequence, a series of values. Or you may need to subscribe to a series of values, like a stream of updates or something. It's kind of reactive pattern that I think Roland will be talking later. So because we already implemented the notion of virtual actors, we took the same approach to streams. Say, okay, what if streams always exist? So by merely knowing the name, identity of the stream, you can always produce a stream, you can always consume from a stream. And that's effectively what it is. So you can say, I want to have logical streams per user, per device, per session, and then I can just take a GUID or whatever identity scheme I use, and start producing messages to that stream without creating, without mapping to anything. And there is a provider model underneath. So we included some providers, but the community is building more. So this is a very powerful model to implement things like I described, and it's actually used in production already. Anybody knows when tomorrow comes? Eurythmics? Anybody? Okay, I'm alone here. So when we were building this in Microsoft Research, and we had a couple of applications we built ourselves. We built distributed graph database. We built this social graph with developers with a lot of code artifacts. So we've been talking to people internally in the company saying, look, we're building this Orleans, and it seems like it's going to work. We only have some results and measurements. But people didn't believe us. Like, oh, yeah, people tried to do this distributed objects. Yeah, it's a simplistic model. If it's simple, that's not going to work for some serious cases. It's kind of like Visual Basic a little bit. It's hard to convince people until this guy came. Anybody knows Master Chief? Oh, great. Some people do. So the Halo people, like the Hoop Somo who was in the video, they came to us in 2011 and say, look, we have this architecture we want to build for distributed scalable compute on the cloud. And we discovered your work. It looks like Orleans covers 80% of what we thought we needed to build, and much better than we thought we would build it. So let's collaborate and fill the remaining 20%. And by the way, we need to be in production in 3 months. That's a real story. That's why I turned to my team and said, these guys are crazy if they want to go in 3 months in production with technology from Microsoft Research, but let's drop everything and help them. And that's how we put the first service online. There was Halo Reach Anniversary Edition. They liked the experience, the developer experience so much that in 3 months, they could go to the cloud and build it. So that for Halo 4, that became the standard. All services for Halo 4 were built on Orleans within like 6 or 7 months. With a very small team, they put everything. And it worked beautifully. Then other people started coming. First gamers, because they see, oh, if it works for Halo, I'm much smaller. Anybody played Age of Empires, Castle Siege? So it also runs on Orleans. And after gamers, it's usual in our industry, non-gamers started coming. We have some services in Skype, several services in Azure that do monitoring. There's this interesting IoT project of launching balloon to almost like 40 kilometers in stratosphere. But also some projects that in the works, like these applications that built into Windows, or it used to be called Bing apps, MSN apps. They may be not the fanciest, but they have hundreds of millions of users behind them that use these applications. The services that serve data for them, they need to scale. So they also go into production soon. And Gears of War ships this fall. So this is just some examples of them. But if you look holistically at the problem space, and you talk to all these analysts and specialists, they like this notion of the magic quadrant. And I thought, well, why can't I have Sergey's magic quadrant? So I put my own quadrants. So bear with me. So the one corner here, one quadrant is interactive entertainment, which includes games, but not just games. So people move to interactive television, where you can pick and choose. You can personalize the delivery. So you need to have this low latency, high throughput personalization experience. Another bucket is near real-time analytics, where you want to process in the near real-time events and signals coming from software or from devices and make decisions very fast, alerts, whether something is going wrong, I need to do something. Fraud detection is a good example. And it's another case where fraud detection in credit card industry is actually not that different from fraud detection in gamers, where they want to detect people that misbehave and ban them so that they don't pollute the experience for the rest. So that's the same thing. What you need to have a lot of context is, so you have a context of a user, you have context of a session, and you can make these computations within that context and raise flags and send the signal, say, hey, I think this user is going badly, or this credit card transaction is suspicious. Run it through the same sort of logic. Experimentation and flighting, where you change the tweak experience for a small percentage of a user, analyze if it's better or worse than your normal, and then decide to switch to it. Then the hottest quadrant, that's I think why I put it as red, is IoT. Everyone is in IoT, everyone wants to do it. But it's kind of the same thing. I already mentioned that it's similar to social network, where you have a context of a device, you have control over a group of devices, you have the signals that a lot of commonalities actually between these quadrants. And then of course I need the bucket for everything else, because you can put almost any distributed computation in this kind of system with these patterns like to fan out and coordinate computation. You can build a lot of real-time collaboration scheme, for example. This is a question? Oh, yes. I'll buy you a beer. We open sourced Orleans in January 2015. I wish we have done it earlier, because we wanted to be there. And then in today's world, if you're building an infrastructure, if you're building framework for a cloud, nobody really going to seriously go in production if it's not open source. Because you bet in your business and you can't wait for somebody somewhere there in Redmond go and fix the bug for you and have it fixed 2 months later. You want to have this assurance that that you can fix it yourself if necessary. But that's much more than that. The experience of going open source way exceeded our expectations, like, absolutely astonishingly. People in the company and like on my team enjoy working in open source so much that I had no problem hiring people. I just hired 5 people to my team, and one of the things I was selling to them is like, look, you're going to be paid to work in open source with all these people, very passionate people around the world. They're going to help you, going to submit their fixes, we're going to share their ideas. And you paid for it. And at the same time, you're building your resume for your future employers, because 5 years from now, 10 years from now, when people ask, instead of your resume, they'll ask, what's your GitHub profile or some other profile? I had no problem filling these positions, believe me. But really, it's such a rewarding experience of working in open source. But now with .NET CoreCLR going cross-platform, as Orleans becomes compatible with CoreCLR, becomes cross-platform as well. So pretty soon you'll be able to run it on Linux or Mac OS and anywhere. It's also exciting to say, like, we're open. If you love somebody, set them free. Anybody? Thank you. Great. We're doing better. We'll have more beer. So this is our GitHub page. So what's important is that Orleans is not tied to anything. It's not tied to Azure. Some people misconstrue that. It's not really locking in into any technology. Yes, we use .NET because this TPL is so great, like we're doing this task, the sync await. But really, then customers run AWS. We have these modules that are built by people in the community for Zookeeper, for Protobuf. So you can run anywhere, really, wherever you want. What I'm most proud of is we also have a Jvm clone. Because Microsoft is notorious to being fast follower. In this case, we have fast followers in JVM. So Orbit, this is built by people in the Bioware company, part of Electronic Arts. They told us, like, when they look at Orleans, when we published the paper and started talking about it, they were blown away by the model, by the programming model. But because they were JVM shop, they couldn't use .NET at the time. So they just built a clone in JVM, and they like it, and we love it. There's Roger Elsing that is trying to build something like that in Go right now. We moved the project about 18 months ago from Microsoft Research to Product Group, and we continue building within Microsoft Studios Product Group. But we continue collaboration with research, so we're not stopping. We're building more functionality. The one thing that is being merged, yes? Yes? More beer. What I described before was that Orleans runs on a cluster of machines. So you have a cluster of VMs and you run it. This takes it to the next level. Instead of running a single cluster, you run what they call multi-cluster. So you can deploy to different data centers and run it as a single application, a single service. Instead of failing over or having multiple instances of routing, you run it as a single service. But you have locality. Your Australian users can talk to your Australian data center and a cluster there. Your European users can talk to European data center. But all this works seamlessly. And if one data center goes down, your code, your execution migrates to another data center, just like within a service within a single cluster. So this is another project that is led by famous Phil Bernstein. I'm sorry, he's adding ACID transactions, and you have very promising results of transactions that span grains. It's a great work. We hope to get it in once they have resources to finish it. So it's just accelerating. We're not stopping. We're moving faster as we should. Clicker. So we go back to this picture of what business needs. It's time to market, ROI, all these concerns that translate into developer productivity, scalability, and efficiency. I dare to claim that we cover these three things with Orleans. Of course, we didn't solve the world hunger problem. Of course, there is more to do. But I think we made a significant step in that direction. And as I understand, you're mostly JVM people. But no, .NET is open source. .NET is cross-platform. There is already a release candidate 2, and RTM will be very soon. So you can already look and run it anywhere you want. But also you have the option of running Orbit, right, the JVM solution. But even that, even if you don't take technology, my sort of thing for you to take away is look at the lessons we learned. Look at this approach of using, some people call it context-centric computation. You don't have to call it actor model. You can have different implementations, but look, maybe benefit from lessons we learned and mistakes we made and corrected. That's kind of what my message to you, that it helps to question the common wisdom, like we did with actor model. With certain people thought that you have to have supervision trees like in Erlang. So we think we've proven that it's not necessarily the case. You can have a much simpler approach and benefit more from it. That's kind of what my takeaway for you is. Led Zeppelin. Who said Led Zeppelin? More beer. And if I can click, thank you.